Okay, so my name is Chris Byrnes. I'm from the University of Sussex, and thanks to the organisers for inviting me to give this pedagogical introduction to primordial black holes with a focus on newer developments. This is something I've been working on with fantastic 25 co-authors over the past 14 years. Okay, so why study primordial black holes? Well, I hope you'll watch this talk because it's a way to probe the initial conditions of the universe and what is the universe made of. Black holes are certainly cold and dark, but astrophysical black holes form too late to be the dark matter, certainly after this cosmic microwave background formed, while a primordial black hole is a viable dark matter candidate. Okay, so a primordial black hole is a black hole which formed in the very early universe, typically thinking less than a second after the Big Bang. Notice this property that the black hole radius scales like the mass, the Schwarzschild radius, right, being proportional to the mass of the black hole. So if you treat a black hole as a uniform mass sphere, of course it isn't really, but if we treat it that way, we can think about what would the density have to be, and we have this curious property that the density is inversely proportional to the mass squared. So the lower the mass, the greater the density. In fact, supermassive black holes are really not very dense, in this average sense. Now in astrophysics, from standard model, from degeneracy pressures, we have a maximum possible density, which implies a minimum possible black hole mass. Somewhere around the Chandrasekhar limit, okay, around the solar mass. In fact, a bit above, because those would be neutron stars. But anyway, they're still compact objects which form gravitational waves. To see a compact object merge and know it's a primordial black hole, it should be really, well, at least one way would be to see that it's clearly subsolar. Then there's also the possibility of really much, much, much lighter primordial black holes, because the early universe reached arbitrarily large densities. And so there's a possibility of those evaporating today, which would then generate particles at an arbitrarily high energy. So, having motivated primordial black holes, hopefully you're still watching, I want to cover a lot of topics in less than 40 minutes. So briefly, to summarize again, primordial black holes can be the dark matter. They're an interesting candidate, which is not a new particle. There are, though, challenges associated to their formation and probing the small scales. Then going from sort of heaviest to lightest mass, we'll talk a little bit about supermassive black holes, then the LIGO-Virgo-Cagra range, which has this nice coincidence of scales related to the pulsar timing array and to the QCD transition in the early universe. The asteroid mass window, being the one where you can have all dark matter in primordial black holes. Then we'll talk about evaporation and relics as another less frequently studied and less appreciated possible dark matter candidate. Finally, if black holes are some fraction of the dark matter, then there's the interesting result that you cannot have both WIMPs and primordial black holes, at least for the fiducial WIMP. Let me be clear and apologize that there are only so many things I can mention in a talk. Also, there are only so many things I know about. So I will miss references, I will not state all the caveats, and there will be topics which I simply don't cover. And again, I apologize if I don't cover your favorite primordial black hole topic. Inevitably, I'm focused more on the things which I know best about, which is the things I've researched on myself. Okay, so dark matter might not be a new particle. I want to be clear on that, because there have been contradictory claims in the past saying that we've closed all the windows, that dark matter cannot be purely primordial black holes. But really that's not the general state of consensus in the community. So here's a simplified set of constraints. Of course there are many others, but this is one of my favorite plots from Green and Kavanagh, a nice review article, where they show on the left-hand side, so evaporation. So if your primordial black holes form with a mass only a little bit above 10 to the 15 grams, which is about 10 to the minus 18 solar mass, then they would be getting towards the end of their lifetime today. If you put the age of the universe equal to the to be equal to the black hole lifetime, you're about 10 to the 15 grams. So those which are heavier by 1 to 2 orders of magnitude will be evaporating enough to be detectable via their evaporation products. Then you've got the asteroid dark matter window, and then to the heavier end you've got microlensing constraints. Microlensing coming from a whole range of experiments. Which mass they probe depends on the cadence, meaning how regularly they repeat measurements of the same background stars to look for a sort of a temporary brightening as some lens, such as a primordial black hole, crosses between the telescope and the background star. To the heavier mass, you've got then constraints from non-detection of, or at least not over-detection of gravitational waves, perhaps more model-dependent constraints on accretion, and dynamical constraints related to, say, large-scale structure, galaxy formation, etc. So the vertical axis, I should have said this first, is FPBH. So FPBH equals 1 means all the dark matter in primordial black holes, 10 to the minus 2 is 1% of dark matter in primordial black holes, etc. And near the end of this talk, I'll come back to this possibility of a mixed dark matter model. So we're still interested in the formation of primordial black holes, even if they're only a very small fraction of the dark matter. Let me just focus first a little bit more on this window to convince you that it's hopefully open, despite, as I say, some previous claims saying it had been closed. Also, let me give the caveat that this plot here assumes a monochromatic mass function, meaning a delta function. All primordial black holes have a single mass. Of course, that's not realistic, but nonetheless, a relatively narrow mass function is considered quite realistic if you have a narrow peak in the primordial power spectrum responsible for generating these primordial black holes. But again, not exactly monochromatic. So here's an idea, for example, if their mass function is log normal distribution with a width of 2, which is quite broad, and you can see there's still some open area. See also Gorton and Green for a more recent update about a year and a half ago, showing that it's only when you get to really quite broad mass functions, a log normal with a width greater than about 5, when you can really close the window completely. And you can also see, it's interesting, right, how the constraints, they do change as you go from monochromatic to non-monochromatic, but they don't change dramatically. So you would really have to go to a very extreme, a very flat mass function before these constraints change in the sort of horizontal sense by orders of magnitude. Okay. So here's just briefly what this gravitational lensing is, because microlensing is a very strong part of the constraint. So as a black hole crosses through the line of sight between a background star, typically, for example, the Large Magellanic Clouds or Andromeda Galaxy, it will temporarily look brighter and then go back to looking faint, well, to looking like its original magnitude. Now, the mass gap, these asteroid mass gap black holes have atomic-sized black holes, and their Einstein radius is also very small. So you cannot really resolve the Einstein ring, that's for sure, of the star behind. What you do see just is this temporary brightening. Now, you do, though, need that to be at least, the effective Einstein radius to be at least as big as the apparent size of the background star. Otherwise, you can't magnify all of the background star at the same time. And then the brightening, the relative brightening, it becomes almost negligible and simply cannot be observed. So this is one example where, using this point source approximation in this figure from 2017, you can see it looks like the entire window had been closed using a combination of femtolensing. That's, though, a forecast, not a constraint. And this is a complaint in the field, that sometimes some of these plots made on constraints do not clearly distinguish between what are current constraints or what are forecast constraints. So there's no current constraint from femtolensing. And from the point source approximation, you see that you could constrain much lighter black holes whose Einstein radius becomes so small that, in fact, it wouldn't be able to lens the whole of a background star. Okay. Should also say that there are detections in microlensing. A very recent paper from Sugiyama this year had 4 to 12 candidate lensing events, depending on the significance you want. That's interesting, of course, but one has to be very cautious in knowing or, claiming a detection of primordial black holes, because there could be other sources such as free-floating planets which generate the lensing event, whose mass would be in the right mass ballpark. Okay, let me say a little bit about a primordial black hole formation. So the normal picture, normal in quotation marks, of course, who are we to say what is the correct mechanism? But the most commonly considered in the literature mechanism is that you have large amplitude density fluctuations, small scales but large amplitude, which then collapse shortly after horizon entry. It can't be before horizon entry, because then causality means that basically gravity can't know you're in an overdense patch and it'll make the whole thing collapse into a black hole. Once you do re-enter the horizon, if you've got an overdensity of order 40%, say, which of course is huge compared to the CMB overdensities of order 10 to the minus 4 or 10 to the minus 5, then you overcome the radiation density, the radiation pressure rather quickly, and form a black hole in of order 1 Hubble time or 2 Hubble times. Typically this does require fine-tuning, especially in single field inflationary models, or at least a large sensitivity to the model parameters, because if you have some so-called ultra-slow roll period, I won't go into the details, but the power spectrum grows very, very rapidly during this time. And so if you have ultra-slow roll while the field is slowing down extremely quickly, phi dot goes like a to the minus 3, well, you have to be very careful. If it's very short, then you just shoot straight over it and nothing interesting happens. If it's long, then you get trapped and you reach eternal inflation, which is, of course, not what we observe. Something important to stress as well is that if black holes form in this picture, again, via a large amplitude peak with large amplitude fluctuations already at horizon entry, whether that's generated from inflation or your favorite alternative inflationary model, there will always be a one-to-one relation between the horizon mass, the black hole mass, which is of the same order, the co-moving Fourier number k, the time of formation t, or also you can map this to the energy scale, etc. Now, there are extensions where you, for example, don't have this large radiation pressure if you're in an early matter-dominated era. Then naively it should become much, much easier to form a primordial black hole because there's no pressure to resist gravitational collapse. That's true, but on the other hand, then non-spherical effects and velocity dispersions, etc., mean that you can't just say, the critical threshold goes to 0. That would only be true if you had perfect spherical symmetry, etc., which we know in the real universe you don't. Okay, so again, why do we study primordial black holes? Well, apart from them being a unique dark matter candidate where you don't need a new particle physics, particle, it's also to probe all the scales of inflation and to probe the universe on small scale. So again, learning about the initial conditions. We know from CMB plus large scale structure what happened on the largest scales with very high accuracy. Right, Planck plus ACT, SPT, and all the large-scale structure surveys tell us that with high accuracy, but unfortunately, in terms of primordial physics, we learn very little. We learn the amplitude, we learn the spectral index, of course they're very important. We have an upper bound on the tensor to scalar ratio, but that's about it. We don't have detections of more parameters. We do have constraints, yes, but not detections. So potentially inflation was very close to exacta sitta for those large scales, but then did something more dramatic. For example, ultra-slow roll, or in multiple fields you may have turned a corner and then something more interesting may happen. You may generate a peak on the smaller scales where it's much harder to probe. So how can we probe them? Well, you need a relic, something which survives from the early universe. So a primordial black hole is the one I'm most interested in, but also stochastic gravitational waves, or perhaps topological defects, which I'm not going to talk about in this talk. Okay, so here's an idea of these initial conditions. So on the very large scales to the left, the green band shows where we really have a detection from CMB plus also large-scale structure going down to scales of approximately 1 megaparsec. Then to slightly larger scales, we've got good tight constraints from mu distortion, from the CMB FIRUS. There's the Kobe FIRUS instrument on mu distortions, and also from the pulsar timing array, which is rather new. And the red and the blue lines are the required amplitude to generate primordial black holes at the current upper bound on their allowed existence. Notice how those lines are nearly flat. They only vary by less than an order of magnitude over a huge range of mass and of physical scales. Again, remember, for any given scale, there's a given horizon mass, which gives you the primordial black hole mass. Why is the variation in those primordial black hole lines so small when the constraints on FPBH are so large? Well, sorry, the variation in the constraints, especially to the light ones which evaporate, that line goes well below 10 to the minus 4. Well, it's because it turns out that you're exponentially sensitive to the amplitude of the primordial power spectrum to give you the value of FPBH. So when you invert that, you get only a logarithmic, a weak sensitivity. So that means these constraints in the primordial power spectrum, the amplitude of that, or the variance, are really not very sensitive to the exact details of, exactly what the FPBH constraint is. And in fact, if you come down just by a factor of a few from those blue and red lines, then the number density really goes to exactly 0 inside the entire observable universe. Okay. Why are there two lines? Well, the red line is for a rather narrow log normal peak, the blue line is for a broad peak. So you're more sensitive, in fact, to the width of the primordial power spectrum peak than you are to the value of FPBH within reason. Okay, so going now from heavier masses to light masses. Well, supermassive black holes, they're detected in the centers of many, I think, most galaxies. They're hard to form astrophysically, but they are seen even at high redshift, for example, with JWST. Exactly how high is not still disputed, but certainly they must reach masses beyond 10 to the 6 solar mass in less than 1 billion years. And even using very efficient accretion, this is seen as challenging. So to quote from people who do know about this field, a voluntary et al. Review, low mass seeds are common, but high mass seeds are rare and depend on processes which may be possible, but we have not yet observed. And to the best of my knowledge, that's still true today in 2026. Okay, so an obvious idea then is we have this mystery of how did the supermassive black holes form, is let's say that they're primordial black holes, or at least that the seed is primordial. Can you do that? Well, it depends on what mass seed you need, or you want. So the very big challenge are spectral distortions. The spectral distortion, the mu-type spectral distortion, chemical potential related of the cosmic microwave background, which essentially is a perfect black body, up to better than 1 part in 10 to the minus 5, no detection from a black body has been ever detected, is shown by these red lines here. So the red line is the constraint on the variance of the initial conditions from the fact that we haven't observed a deviation from a spectral distortion. And why would you have them when you've got large amplitude perturbations? Well, it's because you have this baryon photon plasma sloshing around with gravitational perturbations, of course, pulling things in and pushing them out. Well, radiation pressure pushing them out again, and that would create damping, which would create some heating of the plasma in a way which can no longer thermalize over a given range of scales and temperatures. So you can see this red line is very tight. It comes down to a constraint of 10 to the minus 5, which is tighter than the the required amplitude to form even just one primordial black hole in the entire observable universe, shown by the solid green line if your initial conditions are Gaussian distributed, and yes, a much lower amplitude, but still larger amplitude than the mu constraint line if you have a Gaussian cube distribution, so a very, very, very highly non-Gaussian distribution. Gaussian cubed is the infinite GNL limit, which is frankly not realistic. There's no actual model of inflation that I know of which would give you that. But even in that case, you can't generate any primordial black hole seeds of like 10 to the 7, 10 to the 8 solar mass. And we do observe supermassive black holes that massive. Being perhaps more sensible and trying to form, say, FPBH of around 10 to the minus 10, you can see that you can have seeds of around something like 10 to the 4 solar mass, where the lines intersect on the right-hand side, but not heavier. Okay, this may still help, but you still need a lot of super Eddington accretion to get to the required mass. Okay, and that's going back a long way from results from Nakama et al. And most recently, myself with a group in Aachen, Sharma and Lesgurg, plus Xav Pritchard. In this plot, I showed how to generalize the mu distortion constraints to non-Gaussian initial conditions. Okay, now if we come down in mass to the range probed by LIGO, Virga and Cagra, gravitational wave detections, well, these detections are in fact responsible for primordial black holes becoming such a huge topic. Partly because the masses of the initial black holes seen merging were a bit unexpected, and also they all, or not all, but the majority seem to have very low spins. Rather different from the black holes seen previously by astrophysical means of sort of accretion disks, which seem to be rotating very rapidly, often close to maximally rotation. However, a Bayesian model comparison, first done by led by Alex Hall from Edinburgh, together with Andrew Gow and myself, and then done in much more detail and also allowing for mixed components of astrophysical plus a primordial black hole, does not favour the majority being primordial black holes. But there could, of course, be a subdominant component, for example, filling the mass gap windows, certain masses where you don't really expect to form compact objects through astrophysics. You can treat this more optimistically than I do personally, the so-called positivist perspective of evidence from Bernard Carr, Sebastian Kless, Florian Kernel, Juan Garcia Bellido, etc., and Michael Hawkins as well. And so I refer to a big review by them. And this is not the only piece of evidence, or at least suggestions for detections of primordial black holes. I've also mentioned microlensing. Okay, so let me show you an interesting link to the QCD transition. It's not a real phase transition in the sense that it's not first or second order, but nonetheless, it's smooth, but nonetheless. We know from standard model physics that when you reach a certain temperature of the QCD mass, where the quarks get bound together into hadrons, that the equation of state softened. And when the equation of state softened, then the equation of state drops from 1/3 during pure radiation domination to be less, down to about 0.25. Okay? And you might think, well, that's not a huge reduction. It's certainly getting nowhere near to early matter-dominated era. That's true. But nonetheless, because you're exponentially sensitive to the collapse threshold, which is approximately linearly sensitive to the equation of state, again, not as you go to the equation of state going to zero, but for still relatively large values, well, you can look at this primordial black hole mass fraction, where the dashed line on the right-hand plot shows you if you were with an equation of state of 1/3, and when you allow it to soften, you see that the number density of primordial black holes grows by potentially 3 or so orders of magnitude. So that's a lot. You still need the primordial power spectrum to be boosted by many orders of magnitude compared to 10 to the minus 9. But if that is the case, then there's a reason at least to find a peak where by very nice coincidence the peak is at approximately 1 solar mass. Remember, related to the Chandrasekhar mass, but with a good tail to smaller masses. The sorts of masses where you really can't form any compact objects in standard astrophysics. So there's a real hope, and I'd be delighted if LIGO Virgo Cagra can detect and do detect, because they are searching for subsolar mass primordial black holes, which then really should be primordial. Let me just mention, so a few other people have done this more carefully since this older work I was involved in. So Franciolini, Escriva et al. Did numerical simulations, also with Ilio Musco. And also, if you have very broad peaks, then you also have to be careful about other constraints, such as the mu distortion constraint on the impact of the pulsar timing array, gravitational waves, etc. So using these very broad mass functions, the sort which I'm showing here, does come with challenges. Hey, having mentioned pulsar timing array, here we go. So this was one of the big news of the last 5 years. The first ever detection of a stochastic gravitational wave background in June 2023. The expected signal is astrophysical. It's supermassive black hole binary in spirals. Not watching actual mergers of supermassive black holes, but the stochastic gravitational wave background from lots and lots of supermassive black holes, which are very, very slowly merging over a very long time scale. There were a huge flurry of papers about that, and of course it may be astrophysics, but already in the original papers they were showing that there are some hints for new physics, in the sense of the frequency dependence of the observed gravitational wave background doesn't perfectly fit what had been expected. Now, again, astrophysics is complicated, messy, and it could well be that that's the true solution, but there was a lot of interest in new physics being the solution. So what's that got to do with primordial black holes? Well, at linear order, scalar and tensor perturbations are decoupled, but at non-linear order, scalar perturbations squared generate second order tensor perturbations. Yes, they're not huge, but when your primordial power spectrum grows up to something like 10 to the minus 2, then the second order gravitational waves become significant, as shown in this formula in the box. And I refer you to Guillaume Domenech's nice review on this stochastic induced gravitational wave background. So to show this plot again of the initial conditions of the universe, as shown by the arrow, then you've got this nice coincidence of scale. So the pulsar timing array has detected gravitational wave background, maybe astrophysical, but if it's not, its amplitude which you require from the primordial scalar spectrum when you do the calculation is almost exactly the same amplitude as you need to generate primordial black holes, and their mass is around the range seen by LIGO Virgo Cagra, and that's also the QCD scale. So all of these things come together in a very interesting way. Whether the details exactly work is not yet fully agreed upon. Certainly it's challenging, but it's also tentative, but it's also very exciting, right, to see all these different scales potentially come together. And well, time will tell. And also there, of course, there's more pulsar timing array work going on. It's a slow game, but we will see whether the evidence for them being supermassive black hole binary or something else, gets how that gets resolved. Okay, I'm now going to move on to the evaporation. So again, now thinking about primordial black holes much lighter than I've talked about so far. Initially, those with 10 to the 15 gram approximate mass would be exploding today. This is based on the Hawking semi-classical result that the temperature goes like the inverse of the mass. So you can integrate that up using the blackbody spectrum to find the lifetime is proportional to the initial mass cubed. Okay, so as they explode, the temperature essentially goes to infinity as the mass goes to 0 or up towards the Planck scale. So you would have this sort of runaway process where you generate more and more high energy particles until that all ends. And you've probably heard of this ultra high energy neutrino, this 150 peta electron volts, just mind-blowing energy. And the optimistic view shown in this Klipfel and Kaiser paper last year was that this is an evaporating primordial black hole, a standard primordial black hole following Hawking evaporation. However, shown relatively shortly afterwards in this another paper by Aroldi et al., was that such a bright event, this black hole final explosion, should be very bright and should generate lots and lots of particles. And yes, the KM3 net may have seen one, but IceCube, which is a bigger detector, should have seen lots of neutrinos, and LASO should have seen both gamma rays and protons. Another detector called Hawk was switched off, unfortunately, at the time of this explosion. Now, that's not the end of the game. You can have memory burden, or if you add large spin to the primordial black holes, or extra dimensions, etc., or new physics, then you have more freedom to try and resolve this apparent contradiction of having seen one very high energy event but not lots of other somewhat lower energy events. But challenges remain. And just to explain sort of this plot briefly, why would you expect to see huge numbers, like 1 million photons at lower energies just approximately 10 hours before the final evaporation? Well, if you do work out what the mass would be at the time of forming 150 PeV neutrino, and then say, well, how much heavier would it have to be to form, say, an MEV neutrino, for example? I'm slightly making up numbers, or a gamma ray. You find that the mass is, of course, many orders of magnitude larger when the temperature is many orders of magnitude smaller. And that means it's got all of that energy, many orders of magnitude more, to evaporate. And so you should get many, many more particles at a somewhat lower mass and a lower energy than you would get right at the end of the evaporation, when the total energy left to evaporate is, relatively speaking, small. Again, of course, there are caveats, depending on how simple your primordial black hole model is, or the evaporation process is. So again, for the sort of fiducial Hawking evaporation, nothing else, no spin. And it is reasonable to think that typically the spin will be evaporated away more quickly than the mass, meaning that a black hole which is initially spinning will typically settle down to be non-rotating before its final evaporation. And remember, we're talking about a black hole which has survived the age of the universe and exploding today, so it has had a long time to evaporate away its spin. You can see here in this plot then, to reach the 1 PeV scale and above, we're talking about the last minute of the lifetime of a standard black hole. Okay. So, other ways to potentially look at that, ultra high energy neutrino, are also to think about the asteroid mass window, and the lower band, remember, is set by evaporation. So evaporation, Hawking evaporation, of course, it's not something which has been observed. It's a theoretical idea. So when in extra dimensions, ED for short, well, extra dimensional black holes are colder and longer lived than the standard 4-dimensional ones, which widens the asteroid mass window, depending on the scale of your extra dimensions, which is this lowercase l. So if L is about as large as is still allowed by observations, tabletop experiments of 10 to the minus 6, this is in a Randall-Sundrum brainwell model, then there's a large range of scales where, a much larger range of scales than before, the 4-dimensional case shown at the back of this plot, where, the black holes would not yet have evaporated or not yet be visible evaporating because they're colder and they're longer lived. And indeed, these extra-dimensional black holes could truly be extra-dimensional in the sense of the black hole radius being smaller than the radius of the extra dimension. Again, as long as the extra-dimensional scale is relatively large. This is also true for the memory burden, the suppression of evaporation from entropy effects as far as I know, first posited by or hypothesized by Guillaume de Varley in 2018. Now, whether this truly widens the asteroid mass window or not depends on the details of how the transition occurs from Hawking to memory burden. And I cite two different papers which appeared at the same time with rather different conclusions, and of course refer you to Zanderdesky's pedagogical talk, who's an expert and who's going to focus on the memory burden. So I'm excited to watch that myself. Okay, now, as I mentioned, the asteroid mass window is certainly still open, shown in red, but there's another mass window where FPBH can be one which is not very often considered or discussed, the relic mass window. In order to be there, you need essentially two things. You need that primordial black holes do not evaporate to nothing, well, just to radiation, but that they leave a nugget, which could potentially, for example, solve the information paradox. What happens to the information as it's evaporated? There are other solutions, but one idea is the relic, that it leaves a sort of Planck mass relic. In any case, the Hawking result is semi-classical, so at some level it should break down, whether that's by memory burden or something else. So if a relic does remain, and if you also did have primordial black holes which form sufficiently light such that they fully evaporate well before Big Bang nucleosynthesis, and it is possible that all of the dark matter are in primordial black hole relics. And this really is a nightmare scenario because they will be electrically neutral, and it's unclear if we can ever probe these observationally. Their number density will be very low by particle physics standards, of course, by the standard, for example, WIMP searches, where you would have a massively greater number density simply because their mass is greatly less than our Planck mass. So that would be a challenge. This is a plot shown here by Amira Al-Jazari. So, well, what is the dark matter? Well, is it a relic? We might never know. Is it a WIMP? That's certainly under observational pressure. Is it a asteroid mass primordial black hole? I'll argue that we can rule that out or detect that in the foreseeable future. But there are lots and lots of other particle ideas, and there's no reason why all of the dark matter should be one thing. Right now, standard model and baryons are certainly not all one thing. Neither is radiation. We've also got neutrinos, not just photons. Okay. So if we do have a mixed dark matter model with primordial black holes plus some particle dark matter, then there's this interesting result that WIMPs, or at least the standard fiducial WIMP with the weak annihilation cross-section, are incompatible with the rest of dark matter being primordial black holes, as long as they're not very light. Okay, why? Well, because you would have very high density dark matter profile around each primordial black hole. The profile goes like R⁻⁹, and the density today compared to the critical density goes above 10 to the 15. And that's why they're really up to what we could simulate. So if we detect WIMPs, even a small fraction of WIMPs, then that rules out primordial black holes. Vice versa, the detection even really of one primordial black hole would rule out the existence of a standard model, the simplest WIMP. It's also worth saying that the dark matter halos, even if they're not WIMPs, and that's really ruled out, but if they're any different dark matter halo around a black hole, could be used to test if a black hole, which is not obviously too light to be an astrophysical black hole, is primordial or not, because the dark matter density profile around a primordial black hole will be much denser and steeper than that of an astrophysical black hole. Why? Well, because the primordial black hole formed much earlier when the background density was much higher, and so it can start forming this dark matter profile around it, this dark dress, at much earlier times. And it will hold some of that till today. And so looking at gravitational wave emission of an extreme mass ratio in spiral, a so-called EMRI, with, not in the near future, but for example with LISA, may be able to tell us what the dark matter halo is around a black hole. So the dark matter search certainly continues, and again, a primordial black hole, I'm not saying it's the best candidate, but I'm saying it's it's a special candidate. Will we ever know? Well, maybe not of their relics, maybe not of their gravitinos, but though I know nothing about gravitinos, but if it's in the asteroid mass, I think the answer is yes, because a combination of improved mu distortion constraints and improved pulsar timing array, for example, with the square kilometer array, plus LISA or Tianjin or other, very long baseline gravitational wave experiments, plus something like Einstein telescope, together will provide such a strong constraint on secondary gravitational waves that we should really detect the primordial power spectrum or rule out the required amplitude to form even really just one primordial black hole inside the entire observable universe. There are caveats. Again, I'm assuming the standard formation mechanism, which I described at the top, near the beginning of this talk, and also assuming Gaussian fluctuations. If they're non-Gaussian, things change, but typically not by enough to change this conclusion. So to summarize, primordial black holes are still a viable dark matter candidate in at least 2 mass windows if relics exist. They can form with any mass, unlike astrophysical black holes, so they probe the initial conditions on small scales. There's a potential link to supermassive black holes, although that's, to be honest, very difficult because of the mu distortion constraints. Potential link to LIGO-Virgo-Cagra gravitational wave detections, to stochastic gravitational waves, for example, pulsar timing array, to evaporation, to the dark matter dress, etc. You can reach arbitrarily high energies in the final explosion, but you need to do something beyond the standard Hawking evaporation to explain the KM3 net, ultra-high energy neutrino. And finally, the good news is that we should at least be able to detect or rule out primordial black holes as dark matter, or even as down to a negligible fraction of the dark matter, within 10 to 20 years using things like LISA. So thank you for watching.